Hello, welcome to another Cosmology talk. Today we have Eloisa Bentivegna, who is a research scientist at IBM. This will be the first talk in what will hopefully be an ongoing, sporadically updated series of underappreciated papers of the past. Eloisa will be talking about work from 2012 and 13 and following years, with the work culminating a little bit in a 2018 review paper, although there's been work since then as well. The 2018 review paper is worth checking out and is linked in the description. The work she's trying to do is something really, really interesting. So as she explains in the video, normally when we think about the metric of the universe, we think of FRW, Friedmann-Robertson-Walker plus perturbations, which is the metric for a homogeneous and isotropic universe. And this does seem to match the observations with at least a minimal number of new parameters. But we also know if we zoom in far enough that the Schwarzschild metric should be correct around isolated spherical objects. So somehow we should be able to write the full metric of the universe as a patching together of a bunch of local metrics too. This is a lot harder to do, but it's worth doing, especially to see if and how this FRW limit emerges. So as she says in the video, the FRW dynamics does seem to emerge mostly, apart from maybe some interesting effects to do with the total mass of the system, that individual masses of the black holes going into the system get dressed in some way. So maybe in the age of H0 tensions, this sort of work needs to be re-examined to see if some sort of relativistic effect, maybe just maybe, is responsible for H0 tension. And people are re-examining it with mixed results. So this video turns out to be really technical. I recommend trying to stick with it and getting what you can out of it. There's some really interesting discussions we have during the technical bits, and the results themselves are really interesting. However, if you don't have the stamina to watch something technical, then about halfway through, you can see the timestamp on the screen at the moment, Eloisa's presentation is actually over, and the rest of the video is us just talking much more generally about her work and her job at IBM. This is a really interesting discussion, and especially given Eloisa's very interesting role in the cosmology community as an employee, not of a university or a typical institute you associate with fundamental research, but at IBM itself. But she is genuinely doing cosmology research, numerical relativity research at IBM, and is not, in fact, the first person, as we find out, to be doing such work at IBM. So it would be a shame if you missed that really interesting discussion in the second half of the video because of the preceding technical stuff. And that's it from me. Let's get to the talk. Welcome to Cosmology Talks. Eloisa, do you want to give us a brief overview of the contents of the papers and general questions you were trying to answer?
Yeah, absolutely. Thanks for having me. I will go through some very old set of slides for the sake of historical accuracy. I've tried not to interfere with these slides as much as possible. So you'll see a little bit of the take that we had on these at the very beginning. And the downside of this is that they're not actually terribly updated. They miss a lot of reference to more recent work. But anyway, the paper is this. So it's already, as you see, almost 10 years old. This was essentially the first paper we ever wrote about black hole lattices, a huge contribution by Mikołaj. Essentially, all the theoretical part was due to him. The main intuition that's behind this paper is certainly his. I gave the contribution of instigating the whole thing because I had one major question that at the time nobody seemed to answer except him. And then, of course, we did the simulation and then the numerical work. As I say, this is a little bit of an outdated deck, but it explains well what sort of our objectives and our perspectives were at the time. So the main point was that we were trying to figure out how you could build the space-time representing an inhomogeneous universe. And I think that's obviously the common denominator of a lot of studies in cosmological numerical relativity that have emerged over the past decade. And we immediately realized there were two ways of going about this. The first way was maybe the one that was intuitively more common, or just it was simply more common in the literature, which was to take a completely homogeneous cosmological spacetimes and introduce small-scale inhomogeneities. At the same time, there was what we thought was in some sense an opposite approach, where you would take isolated solutions of gravitating bodies in general relativity and try to stitch them together so that on the large scale, things would look homogeneous and isotropic. And in the early days, we used to show this slide with kind of like this diagram where you really have two scales in the universe where you represent things by either. So on one side, you have a classical isolated body. On the other side, you have a fully homogeneous and isotropic model that you can perfectly well describe at the linear level. And the interesting bit is what happens in between, and you can approach this from either side. And so we try to figure out how you approach it from the left to the right. So one of the things that we identify almost straight away was that there was this old paper by Lindquist and Wheeler in which they had considered how you could put together a system of black holes in a way that it was, at least in some sense, maybe not quite homogeneous and isotropic, but couldn't be considered as in itself an isolated system with an asymptotically flat end. And there were several ways to consider this, to look at this particular system. And there's some of the early works in this are quoted on the slide. The main take that they had was the one of 3+1 general relativity, where you can represent your system as sort of relationships that have to hold on each individual spatial hypersurfaces, plus a set of evolution equations. And so in that particular paper, they concentrated on the relationship that had to be satisfied on each single hypersurface. And so they calculated basically time symmetric or single instant of time, let's say for the time being, configuration of these systems of black holes. Maybe I should go a little bit into this in a very cursory way. So basically, the two equations that matter when you want to build a configuration of gravitational field in general relativity on a single equal time hypersurface are the two at the top. They call the Hamiltonian and the momentum constraint, respectively.
Can you maybe also just quickly unpack what R, K, and D are? People probably are familiar with R, but maybe less so with K and
No worries. So basically, you imagine that at this stage, you have performed a projection of all of your quantities on the three-dimensional hypersurface that represents the equal time surface. So R will be the Ricci tensor of the three-dimensional surface. K is something that's called the extrinsic curvature, which is related to derivatives of the three-dimensional metric tensors in directions perpendicular to this spatial hypersurface. And D is nothing but the covariant derivatives in this space. And then you can make a transformation in the second block, which is essentially a conformal transformation plus a sort of trace/trace-free decomposition for Kij. And then you get the system at the bottom. And this system has particularly interesting both sort of numerical analysis and in general, numerical properties.
So gamma is the metric on the three-dimensional space?
That's right.
And psi is just some real number.
Exactly. So gamma is the three metric on this hypersurface, and it can be decomposed into a conformal factor plus a conformal metric, which is this gamma tilde. And similar, you can pull out factors of psi4, and these are done opportunistically to guarantee that the system has certain properties. You can do the same thing, the same sort of transformation on, for instance, this Aij, the trace-free part of the extrinsic curvature, and similarly to the derivative. So you see tilde everywhere, and every time you see tilde, you're basically referring to conformal quantities, R tilde, etc. Okay, so if you forget the second equation, one of the things you immediately notice for the first equation is that in addition to this system, if you integrate this first equation, you pick up an additional condition. So this is the classical example in the first line. If you integrate this equation for a system of black holes, then you get, okay, so an integral of the terms with the Ricci, the terms with the extrinsic curvature, and on the other side, you have a term where you basically are collecting together both the time component of the stress energy tensor, if you have one, and also any sort of contribution that you might get by doing an integral of the part that corresponds to the Laplacian of psi. So basically, if you have a sort of expression for psi like the one that I have in the second block, and by integrating obviously across it, you can transform these into a surface integral, and the surface integral will just return you the sum of the masses of the black holes. And so on an asymptotically flat spacetime, basically everything is relatively simple because what you will get is a contribution to the masses on a surface around each individual black hole and at infinity. And these two terms will cancel each other. However, if you try to do this in a space that is not asymptotically flat, so you're missing that end, then it turns out that the sum of the masses of the individual black holes is actually unbalanced. And you cannot solve this equation unless you retain any of the other terms. And so on asymptotically flat space, you're actually allowed, you can find solutions that correspond to R tilde equal to 0, K equal to 0, rho equal to 0. If you're not on an asymptotically flat spacetime, then that equation in that case doesn't have any solutions. And so you can decide exactly what term you want to retain into this equation. You can retain the R tilde, the K, etc. And so that was the very initial choice that we had when we decided to look into black hole lattices. Mostly, either you retain the term that has an R tilde, and this means that you're allowed to set the extrinsic curvature to 0. As I say, the extrinsic curvature is related to the derivatives of the metric tensor in the directions that, let's say, is perpendicular to the 3 surface where you are. So in some sense, it's connected to the time derivative of the metric tensor. So basically what I'm saying corresponds to the fact that you're allowed to choose time symmetric initial data. That means, unfortunately, that your solutions will be conformally curved. You're not allowed to use conformally flat if you're using time symmetry. Or you can decide to retain conformal flatness, but at that point, you must absolutely have a K. And so you cannot be in the situation where you select a time symmetric initial hypersurface, or any hypersurface for that matter. And so these are the two main classes of black hole lattices that were considered at the time. And the paper that I'm discussing addresses the first one.
If one was to take the FRW metric that maybe people are more familiar with, and then take hypersurfaces of constant time coordinate, it would have 0 intrinsic curvature, right? But would have some extrinsic curvature. Is that, if you have a flat FRW, is that right? Or
yes, and I'm going to get to it in a second. I've explained this in the case of a system of black holes, but this is by no means specific to a system of black holes. It actually applies to any sort of cosmological model. You, in general, can choose between having conformal flatness or time symmetry, but you cannot have both. And this is well known, right, from the Friedmann class.
Presumably, you could also have R and K non-zero.
Of course, and that is what you will see. So as the black hole lattice starts to evolve, maybe I should say from the very beginning, for the sake of making the correspondence clear, these lattices that we found were the sort of black hole lattice counterpart of closed Friedmann universes. And so, as you know, if you start your evolution from the moment of maximum expansion of one set time, which is a sort of moment of time symmetry, then a little bit down the line, you will have developed a non-time symmetric spatial hypersurface, and you will still have a conformal curvature. So in that case, you will certainly have both, of course. Anyway, the thing that we really liked about this black hole lattices is that you could come up with completely analytic initial conditions. And that's a huge simplification in numerical relativity, because obviously if you have to solve the system that I showed before, it's a bit of a tricky problem. It's an elliptic system. Depending exactly on your boundary conditions, everything else you have in the domain, it may be a bit complicated to find solutions. It may be complicated to find the type of solutions that you want. So having a manner of specifying initial conditions in a completely analytic way was a huge bonus. And this is where Mikołaj's contribution came in. So basically, he worked out that in this case, well, first of all, you can notice the tilde delta is the flat Laplacian. Obviously, we're left with a linear equation. So if we find the solution corresponding to a single black hole, we can just use the superposition principle and build a system of however many black holes we want. And turns out that if you formulate this as a sort of problem on the 3 sphere, so you have the spatial metric that I have in the second block, with this lambda, theta, and phi, which are the coordinates of the 3 sphere, then a very simple solution is just a over sine of lambda over 2, where lambda is the first of these coordinates and a is just a constant. And so basically, you're allowed to just build superpositions of these solutions centered at different values of lambda. And this is guaranteed to be a solution as well.
I'm a little confused by why one can just superimpose solutions.
Yes, of course. So in GR, in its generality, this is not possible. But it's in this very specific case, when you build initial data that satisfies this equation is linear. So at this specific stage, at this specific moment of time, for the variable psi, everything is linear. It's a very special case.
And this phi, is that psi? Or on the previous slide, at the bottom, you've introduced a new variable phi.
Yes, it is. So we use 2 different symbols to indicate that we've transformed the system into these coordinates. And again, the role of transforming into these coordinates is going to be clear in a couple of slides.
Okay, so psi is the actual variable, and phi is psi when it's in the variable lambda theta phi. Okay, cool.
Absolutely, absolutely. So up until the first block, we're constructing things in R3, right? We imagine that we have generalized Cartesian coordinates, if you want, but then you realize that in these other coordinates, there's a special solution. And so just to make sure we distinguish between the quantities in different spaces, we've used different symbols. Okay, so you construct this superposition, and this is completely arbitrary. So you basically have the guarantee that this is a solution for any value of a of I, any value of lambda I, and any value of n. You can put as many black holes as you want. And I haven't quite said why these are black holes. This will come in a second as well. So the interesting thing is this, is that as soon as you start constructing these superpositions, the lowest n ones, if you squint at them for long enough, will actually reveal themselves to be known solutions. So the first one, for instance, is nothing but a coordinate transformation of Minkowski space. And the second one is a coordinate transformation of Schwarzschild. Again, I'm going to give the coordinate transformation on a couple of slides, but notice the correspondence. So basically, we're saying that the solution corresponding to n, at least in these two basic cases, corresponds to known solutions of general relativity with n minus 1 black holes. Why is that? So first, let me say just a quick intermission to this, and then I'll come back to this. So as I said, this superposition is generally for arbitrary ai, lambda I, and then a solution to the Hamiltonian constraint that I showed in the previous slide. Of course, if we're interested in spaces that have at least some degree of homogeneity and isotropy, we want to look at regular arrangement of points in the sphere. And so for that, it actually turns out that there's 6 possible configurations. And the particular one that we've chosen is the one where you have 8 cells. And the paper corresponds exactly to this. Again, this is not a choice dictated by the fact that we wanted a solution. A solution is guaranteed at all times for all configurations. This is just because we wanted to get something that mimicked a homogeneous and isotropic universe as much as possible. Now, going back to those solutions that I have shown at the very beginning, the trick for you to recognize those solutions is to kind of invert a stereographic projection. So basically, it's easy to notice what I've told you, that you can actually recover Minkowski and Schwarzschild, respectively, from those two solutions by inverting the stereographic projection that I'm showing. So those solutions on the 3 sphere correspond to R4 solutions that are transformed according to that law. And in particular, this works if, in that specific case, you put one of the lambda I of that formula at the North Pole, and that's why you end up with 1 fewer black holes that you have on the 3 sphere. So one of the black holes is essentially sent to infinity.
Hello, Eloisa sent me an email correcting a little bit of what she said in this part of the video. Unfortunately, I don't think I understand this watertight enough to paraphrase what she told me like I've done in earlier videos. So what I'm going to do is I'm going to read her email out word for word, just to make sure I get everything correct. In the Minkowski space, the 3-sphere counterpart has one over sign solution, but no trapped surface anywhere. This is because the punctures on the sphere, the 1 over sign terms in the conformal factor, do not necessarily correspond to black hole slices on R3. In the n equals 1 case, that singularity is just due to the fact that the stereographic projection is singular there. So when I say that the black hole horizon in n equals 1 was projected out to infinity, I was wrong. And this is also her words. I used to get the feeling we hadn't fully understood these solutions, and in particular the dualism between S3 and R3 enough at the time. Obviously, that's still the case. So hopefully this is now correct, and I haven't made a mistake because I'm just copying her words. Back to the video.
And what's even more interesting is that the form, once you transform the full conformal factor, and here we go back to psi, we obtain what are known as Brillouin-Quist initial data in numerical relativity, which just represent time-symmetric arrangement of black holes with an asymptotically flat end. So the solution corresponding to n black holes on S3 corresponds to Brillouin-Quist initial data with n minus 1 black holes on R4, or I should say on a hypersurface of R4. This is a solution that you only recover at a specific equal time hypersurface. It's not a solution for the entire space-time. Precisely because of that, of course, once you have the initial data, you still have to evolve everything numerically if you want to reconstruct what happens to the system after that moment. As I said, we picked the n equals to 8 black holes. That was essentially just a convenient choice because the black holes are arranged in sort of particularly easy location, particular symmetric locations when you do the projection, so that it's easy for us to simulate. You can in fact only simulate a quadrant of all this, and it's much more computationally efficient. If you look at this arrangement of these black holes on, say, R3, when you do the projections on the specific initial hypersurface, then you end up with something like this. So you have, as I said, 7 black holes, because after the projection, basically one of the black holes is sent to infinity. The curious part of this is that whilst the black hole is sent to infinity, is the parent horizon remains at a finite difference. So if you activate an apparent horizon finder around that region where you expect it, you actually find a big apparent horizon that sort of encloses the remaining 7 black holes. And this is what is shown on the left-hand side. Okay, and that's basically the main story. I think the initial data were the key part of this paper. For the evolution, we use standard tools. So the Einstein Toolkit, that's essentially a community code, extremely well established for the evolution of numerical spacetimes. Other pieces I had developed within different projects that needed to complement the Einstein Toolkit, where the Einstein Toolkit tends to be a tool for relativistic astrophysics. So sometimes cosmological applications needed extra development. This is the other side of the picture. So as I said at the very beginning, you'd project Einstein's equations, you get some equations that you have to solve for initial data that hold on sort of spatial hypersurfaces, and then you have evolution equations away from those hypersurfaces, and these are them. And so we solve this numerically, and we obtain something like this. In addition to the evolution of, let's say, the geometrical quantities, you also have to specify, of course, how your coordinates evolve from one spatial hypersurface to the next. So this is what came out of that. This was a bit of an iffy part of the paper because if you remember sort of classical numerical relativity, even finding a type of coordinate system that will allow you to evolve a single pair of black holes is quite complicated. So a system of black holes that didn't have an asymptotically flat end was even more complicated than that. And I don't know that we ever got to sort of an optimal solution to the problem. But we had a solution that kind of would allow us to see at least part of this evolution.
Just can I ask you what I think might be it feels like a really stupid question, but you said you have to evolve the coordinates. What does that mean? Because I was under the naive assumption that the coordinates are kind of the thing that you're evolving in. And so if you're evolving coordinates, what does that mean?
Okay, so if you express, a general relativity's equation in covariant form, you obviously don't ever need to think about coordinates. But the moment you project your equations the way I've described, because you want to evolve them numerically, you have to specify basically what spatial and time coordinates are. You normally start by doing this in a single spatial hypersurface. When you move to the next hypersurface, in principle, you have the freedom to change or deform or perturb the coordinates that you use in the first. So you need, in some sense, a way to transport the coordinates from one slice to the next. And again, because of general relativity, you have full freedom to do this. And that is both an advantage and a curse, especially when you're interested in numerical evolutions. You can use this freedom in order to find coordinates that give you the sort of most ideal numerical evolution. But at the same time, if you don't make a sensible choice, then you could risk getting coordinate systems, coordinate transformations that become singular. And at that point, obviously, if your coordinate transformation becomes singular, the metric tensor in those coordinates will become singular, and then you have a big problem. So it's some rope, but you have to be able to use that rope judiciously. So anyway, these are a few quantities that we plotted, some of the observables that we measured during the evolution. But what really mattered in all of this, for the purpose of comparing to the Friedmann class, for instance, was maybe not so much the evolution of quantities in this space-time, so this is various snapshots during the evolution, but how length scaled. Now, the sort of fundamental degree of freedom of a Friedmann universe is the scale factor. And so we had to make a bit of an identification, because obviously in an inhomogeneous space-time, you want to measure this in a way that corresponds as best as possible to the global scale of your system. You don't want to just measure sort of proper distance between points of the space-time that you wouldn't consider, if you want, representative of the global structure of the space-time. And now in these lattices, again, we use them because they were particularly advantageous, particularly symmetric, but there's a clear way to define one such scale, which is the length of the side of a fundamental cell that contains a black hole. And you define these exactly how you would expect. You basically calculate the proper distance, proper spatial distance of this segment. And when we plotted this, we realized that, so this will be the empty circles in this plot, is that these actually tracked closed Friedmann universe quite well, except after we basically lost numerical accuracy because of various reasons, and we couldn't measure things so well. But at that point, the error bars were so large that you can't really say much. We tried a different type of scale measurements, which was the distance between horizons, but that worked much worse. This would be the filled squares. And there's many reasons why that is the case, but essentially the horizons are just not sort of a very good place to measure global scale. They have their own internal dynamics that will get sort of folded into the evolution of the whole space-time. And so you don't really get as clean a measurement as you would have with the edge of a cell. And that's pretty much it. The interesting part, maybe the interesting higher order effect, is that in addition to the scaling, which, as I said, is pretty much tracking the one of a closed Friedmann universe, we measured also a mass dressing effect. So yes, it was true that we could, from a purely kinematical perspective, we could make a mapping between this universe and a closed Friedmann universe, but the closed Friedmann universe that we got as a result was not the one corresponding to the total mass of our space-time, was that one where the total mass was actually higher than what we had. So these were essentially the main conclusions.
Cool. Do you have anything more you want to say?
There's a lot of different things, because both us and other people then went on to study the expanding lattices. So as I kind of implicitly said, these are systems of black holes that start from a moment of time symmetry and then proceed to collapse. Obviously, from an observational cosmology kind of perspective, there's the more interesting, the more compelling cases where you have an expanding lattice. And eventually we did the evolution of that as well. And the conclusions were also quite close, in the sense that we also found that these models tracked their Friedmann counterparts quite well.
I see. And why is it not as simple as just expanding closed universe is just the one you've just presented with the time coordinate in the other direction? Is it not that simple?
But you would have to start away from the time symmetric surface, and we wanted to start from the time symmetric surface. That was a huge simplification for us.
So if you started with an expanding universe and a time symmetric surface, what does that look like? Because you said you match an FRW. What is the FRW version of that?
This will be a flat Friedmann universe, which is obviously always expanding.
Yeah. But always looks like it always did, I guess.
Yeah, exactly.
The next sort of set of questions are what we in 2021 should learn from the work that you did in the paper you've presented, but also the kind of other stuff that you briefly mentioned that you went on to do.
So there were a number of different directions to go from here. So one, as I said, was to try and reconstruct as much of the Friedmann class as possible to see all the different correspondences, see if anything broke, if anything became different from this specific case. And I can't say that we did. It seemed that what we had found for the collapsing black hole lattice was essentially holding modulo higher order effects for other systems as well. And this is quite similar to what other people found. This was also reproduced for things, say, for instance, Friedmann models with a cosmological constant in a number of very different scenarios. And certainly the large scale expansion, never seemed to change too much. The next fairly obvious question from this was to figure out whether any sort of observational property in that universe could be different. And here I'm talking in particular about things like luminosity distance, so optical properties of that universe. And in fact, in a few years from this paper, there was a sort of burst of literature on exactly this topic. Some of it done in numerical relativity, some done with a combination of sort of post-Newtonian and other methods. And for that, things became a little bit more interesting, as you can imagine, especially when you start studying sort of statistics of all possible observers and all possible start and end points of null geodesics of light rays in this universe. Things become much more complex. And so that was also quite interesting.
Like presumably if you start nearer to one of the black holes, things are going to be very funky. And if you start quite far away from them, maybe it's not funky at all.
Absolutely. So the first question you have to ask yourself at that point is, how do you select a representative class of observers? And we put a lot of thought into this. How do you define cosmological observers in these space-times? And in the Friedmann class, everything is fairly sort of obvious and unambiguous. In homogeneous space-times, you actually have to think about it for a little bit. We made some choices, and things did look sort of more interesting than in the other cases. So it's clear what the legacy of these studies at this point are. I think it was really important that the dynamics of such systems, for the purposes of, in reference in the scope of inhomogeneous cosmologies, was figured out. Because as I said, this was one way of starting or asking the question, starting from the opposite end of the spectrum with respect to conventional studies. And so it was important to find out whether there were any sort of contradictions or different results. And I cannot say that that was the case. It seemed that everything matched pretty well, perhaps maybe even too well. So I guess I do have an outstanding question of whether, things there are still corners of these space of models that could be explored, that could give interesting results. But certainly the top motivation for going in this direction has essentially been satisfied, which is to figure out, at least in a few basic cases, how these systems will work, whether you could do it at all, and what their sort of leading order behavior will be.
One of the initial motivations, if correct me if I'm wrong here, but for people considering the impact of inhomogeneities, was that there was kind of a hope that it might be the explanation of the accelerated expansion.
Oh, certainly. I didn't say this at the very beginning, but yeah, so that's kind of like the overarching question there.
And I guess that one of the issues that always came up against, I guess, was that there was an incredibly simple model that sort of fitted most of the data, which is that it was FRW with a cosmological constant. But there's now this H0 problem, right? And there's no very, very simple model that keeps everything homogeneous, or at least allows the FRW metric to survive and still explains the data. So it feels like there might be more scope to reconsider all of the stuff that was going on, trying to explain lambda, with trying to explain the H0 problem now, because there is no simple model, right? There is no cosmological constant that you just put in and everything kind of fits a bit better.
That was certainly at some point. So I think these first studies occurred before the first sort of solid data about a tension between, late universe and early universe H0 started to appear. But as soon as I saw these, I started to become concerned about this, and I know that I wasn't the only one. So there's numerical relativity studies, for instance, the ones by Haley McPherson. They're directly attempting to answer that question: is there any way that inhomogeneous but purely general relativistic effects can model the difference between H0 at various scales? That is certainly one of the interesting aspects to the question right now. That was, I think, even before the data came out, you could imagine that was a very possible scenario, because intuitively you would imagine that part of the reason why a very simple homogeneous and isotropic universe fitted the data so well is just that the data hadn't quite gotten to the level of accuracy where any possible higher order effects would be measurable.
Yeah, and I guess you'd also expect, because the universe is statistically homogeneous, like once you get to the large enough scales, it starts to look homogeneous, that things that only measure stuff averaged over those very large scales might still see the equivalent of an FRW metric. But as soon as you start measuring stuff more locally and aren't managing to average over a large scale, it might show deviation.
There's certainly that aspect, but I think the data that produced the tension wasn't different data. It was data about exactly the same scale, but just much more accurate. And I think nobody's going to argue that in homogeneous and isotropic effect, relativistic corrections to that make a difference. The question is at what scale they make a difference. And eventually, as you go to more and more precise cosmological measurements, you start picking out the difference and you have to include them. That's, I suppose, a very conservative position in the back reaction problem. You will have corrections, and eventually these corrections will become observationally important. It's interesting, it has become important now, and with the...
Potentially important, I guess.
Yeah, exactly. Well,
I guess the most conservative position would be to say that they'd be of the size of the Newtonian gravitational potential, which would be very small and unexpected to be causing this. I mean, that's the most conservative. I'm not saying that's necessarily the correct one, but it could just still be systematics and Cepheids, right? Like,
so I should also say this. So we eventually wrote a review about this, and unfortunately, that there were results about black hole lattices that came out of that. So even the review is no longer complete. But there's a review that you can check out from 2018 that sort of summarizes the state of the art at that point in black hole lattices.
So what I'm very curious to hear about is your current job position and situation and things. You are employed not by a university or a place that most of us would normally think of as a scientific institute, but I think you're about to make the argument that we're wrong in thinking that.
I will.
So you're currently a research scientist at IBM, where one would expect that you'd be researching how to make computers better, but
that's part of the question. So as a computational physicist, because ultimately, I guess, so I have a background in GR and I have a background in cosmology, but by training, I'm the sort of job that I've done day by day for many years. I'm essentially a computational physicist. So as a computational physicist, IBM research is a very natural place to be. There's a lot of people with very similar backgrounds coming from different sides of physics, perhaps. And I should say also, in general, there's computational scientists from many other disciplines, chemistry, the life sciences, etc. So definitely not alone. In fact, the thing that induced me to apply to IBM was that I saw a job advert that pretty much described my profile. They were looking for somebody that was exactly like me. So there was no cultural shift in that specific sense. But it is true that I'm much more interested, I guess, than I used to be, or maybe more interested. I'm more able to dedicate my time to issues that perhaps would have looked too roundabout and distant from the pure pursuit of cosmological results or relativistic astrophysics results. So the idea of just taking a step back and thinking not only about your numerical methods, but also in general about the methods that you use in order to explore a computational method.
So you actually have more freedom at IBM to explore than you would in an academic setting.
Well, certainly more freedom to explore the things I wanted to explore. So perhaps other directions would have less freedom. I don't know, but certainly the kind of direction I had gone down over the years, because I felt there were a lot of questions. We kept, in some sense, going back to those fundamental questions, never really had the time to kind of stop doing the cosmology or kind of stop doing the strictly observational part and think about dynamical systems or control theory, or in general, how you invert large-scale computational model, how you solve the inverse problem. And obviously, we moved from a topic, I'm talking about numerical relativity, we've moved to a field where it was largely kind of direct problems. People wondered, okay, I have two black holes, how do they behave together? Or I have this other system, how does this help? To a system where we're more interested in, I have this observation, what could possibly have produced it? So inverse problems, I think, have increased manifold. The importance of solving this problem has increased manifold in numerical relativity over the past few years, just because of the fact that the field has become much more observationally oriented now, even more in cosmology, I guess. And so that was an aspect that was increasingly nagging me, and now is fully at the center of what I do.
So do you have a job description / direction that IBM pushes you in, or are you kind of telling them this is what I want to work on, and then they either say yes or no, and then you either work on it or don't, or do they push you in a particular direction?
So keep in mind that now I'm in a bit of a maybe special position, because I was awarded what is called the Future Leaders Fellowship last year, by UK Research and Innovation. And that was a project that was entirely designed by me. So I'm kind of maybe on one end of the spectrum. But I would say that there's probably very few people on the other end of the spectrum. It's always a sort of negotiation between you and the business about the things that, where you think you can make the most impact. Certainly, there is a lot of consultation. You're not simply assigned a project, I want to say, or that, that may happen in special circumstances. Obviously, industrial research has got a different business model than academic research does. So I can't possibly rule out things, but in general, you're very much encouraged to carve your own path.
I guess it depends on one's seniority as well, right? Because you just advertise for postdocs. So the ones that you hire, presumably, you might tell them to work on things a bit more specifically than your boss is telling you.
There will be a requirement to do that, but at the same time, the grant is very open on the specifics. As I said, the emphasis is in having computational models that are complex enough and interesting enough to apply certain methods. This is certainly what I've said to people who have inquired about the position so far. There will be a considerable degree of freedom so long as certain prerequisites are met. And in fact, the funding agency itself is extremely serious about making sure that the postdocs aren't simply handed tasks to give, but they have the ability to develop their own independence. As a consequence, they are in a much more senior position when they end their postdoc. So they have a more senior profile in the eyes of the peers and the eyes of the people that will evaluate what their next sort of career step will be. And they're extremely serious about this. We were drilled to no end about the fact that you have to do suitable career development for the postdocs. Yeah.
I guess you mentioned actually before we started recording that it was just a throwaway remark that IBM have more Nobel Prizes than any individual country. Was that right?
So I said that the IBM has more Nobel Prizes in physics than most countries, and obviously not all countries. So certainly my home country. Yes. So you asked me this question, and as I said, I get these a lot. But why would a business be interested in basic science? And the truth is that I think IBM is just a little bit over 100 years old, and you can't really survive as an innovative business if you don't think outside of the box, and you don't have long enough horizons. You can't really do day by day research. You cannot really do short-term projects and expect to survive in those sort of timescales. And if you look at the history of IBM, as a matter of fact, it has hosted very, very notable fundamental scientists in all sorts of. I'll quote Mandelbrot just because it's the first one that comes to my mind. But there's scores of people that have come up with groundbreaking ideas, and these ideas at some point down the line have turned into technologies that IBM developed as part of his offering. So this notion that fundamental research might not look like particularly focused, perhaps, or particularly trying to answer practical questions at the moment, but at some point down the line, it ends up in very, very tangible innovation. It's something that perhaps at the academic level is just recited as a commonplace things, but IBM is extremely aware, and it has known firsthand for a very long time.
Yeah, I guess that that argument, if one can say, look, IBM understands it. When you're trying to make the argument that blue skies research can have very strong practical implications, it might sound like a kind of a stretch, but I guess if one can back it up, then an actual gigantic business like IBM believes it.
Yeah, absolutely.
I guess when it comes to something like cosmology, I feel it's extra surprising because it seems very hard to think of how something would directly come from numerical relativity and then be profitable, right? Like it's not going to be that IBM are going to start colliding black holes for money. But I guess the problems and techniques and solutions that you come up with will be easily transferred to similarly difficult nonlinear systems.
But even before you start going in any specific directions, I think the fundamental idea at the base of this is that it is accepted that you don't know where your fundamental research will take you today. That's it. It's not about sitting down and deciding and trying to figure out now whether that fundamental research is taking you anywhere in particular. Just having that faith to realize, based obviously on evidence of what has happened to ideas that have been formulated within the business in the past, that some of them will take you very interesting places. You don't have to know.
Yeah. I mean, I still come back to that interesting place that might turn out to be profitable for IBM won't be the actual physical consequences of numerical relativity.
Perhaps not. I don't particularly think in those terms. It really isn't a matter of deciding on a practical application of your research today. It's just trying to answer complex questions. And what I want out of the cosmological models that will be involved in the grant work that we'll do over the next 4 years is to have models of sufficient complexity that we can hone methods to search and explore them. And the grant is in particularly trying to address the problem of outliers, of extreme physics solutions, and how you find them, how you find extreme regimes in the solutions that you know, etc. And I think that's an interesting question in and by itself. Yeah, but regarding numerical relativity, I said I was going to show you something. I'm showing everybody something that I think it's a piece of trivia that I found slightly before joining the company. I was for a very long time aware of this paper, obviously, but I didn't realize about the implications until relatively late. So numerical relativists will recognize this. So this is a paper from 1964, which is usually regarded as the paper that started numerical relativity. So this is kind of an investigation of how you might define, of course, the canonical problem in the early days, just because it's the simplest problem, is how you solve the two-body problem in general relativity, and in this very specific case, how you solve it numerically. And the first author is an IBMer, as a matter of fact. So most readers will be more familiar with the second author, which is obviously very, very renowned relativist. But Susan Hahn was an IBMer at the time, and she was part of this picture. So we could say in some sense that numerical relativity was half started at IBM.
Wow. So this isn't a new project for well, I mean, it is a new project, but it's a new old project for IBM.
Exactly. I'm not the first numerical relativist at the company.
So the last question would be, what do you think is a particularly underappreciated aspect of cosmology research being done at the moment?
So one thing that I quite like, and I don't know that I would particularly call it underappreciated, but I know that I would like to see a lot more research on this myself, is that there's been a line of sort of relativistic cosmological simulations that has started from with the idea of a fully kinetic approach, sort of Boltzmann equation-like. So this is where you essentially evolve. It's how can I describe this? So it's sort of a close relative of the particle-based cosmological simulations, but it is one where you simulate the full distribution function in phase space. So you simulate, or you evolve numerically a function that represents the number of particles per volume in phase space, so per volume in physical space and momentum space. And there's arbitrarily old simulations, arbitrarily old studies into this, and it seems things come up and then sort of fizzle off again. And there's been a recent burst as well, and I find this extremely interesting. But for some reason, people like to do sort of quick stab and then it's left to its own devices. Obviously, on its own, it's just an extremely complex and computationally expensive method, but I just wish I could see more attempts in this space. I think there could be a lot of surprises, precisely because I'm interested in, complex models, and I think there's many more interesting things that can happen in a sort of sometimes this is referred to as Einstein-Vlasov, so collisionless Boltzmann coupled to Einstein's equations. For non-relativistic applications, I've actually worked on kinetic approaches in the past few years myself, and I've gotten very interested. It's an incredibly rich sort of type of approach, and one that covers regimes and phenomena that continuum equations simply cannot cover.
And is the problem there that the numerical complexity just gets bigger and bigger and bigger as you get like shells of mass crossing each other? You've then got twice the complexity because you've got to keep account of the fluid going that way and the fluid going that way. Whereas with an in-body simulation, you've just got a finite number of particles and it's the same complexity the whole way through.
At a very basic level, this is just basically for simulations in D dimensions, you'll have 2D direction. So you have a domain that has twice as many dimensions because you have to now calculate gradients with respect to not only the physical coordinates, but also the coordinates in momentum space.
But do you not also get like double valued situations where like there's been a crossing of surfaces?
There's several advantages. So if you can actually afford the computational cost, there's a lot more things that you can do. And that's why I'm saying that these are much more rich than continuum PDE counterparts. So first of all, one of the things that is typically quoted is what you're saying. So if you describe your system as a continuum fluid, you obviously cannot accommodate multi-valued velocities in quantity. So if you have systems of particles that cross, that's a problem. But there's much more to it. So one thing that I think, so this is very well known in classical hydrodynamics, and I think it's even been proven for, or at least sort of demonstrated in some basic cases for Newtonian n-body simulations, is that if you have a pure n-body, so you have a set of particles that move in certain ways, so you kind of relinquish modeling in the full phase space. Obviously, you're going to get very bad statistics from places where the density is low. Whereas if you model, obviously, your full distribution function, you have the proper solution. And so that could be relevant in some specific regimes. But what's even more important, I think, is the question of the limit. So when do you get like a continuum fluid out of this system of particles? And sending the number of particles to infinity is only part of the story. And again, in classical hydrodynamics, this has been explored much more. But what I'm just going to say here is that there's higher ordered hydrodynamical effects that are simply not captured by sort of the Navier-Stokes equations or the relativistic magnetohydrodynamic equations, when in some sense the scale of the phenomena that you're interested in is comparable to the sort of basic granularity of the distribution of matter that you're looking at, then these continuum approaches will fail. And so it's not just a matter of sending the particles to infinity. There's also kind of like a ultraviolet cutoff that you put on your theory whenever you don't do it. So there's several things that you gain by obviously doing this much more expensive approach, but at the same time, you have to figure out how to do the computation first.
Yeah, and I guess as time goes on, you get situations where people do it and they don't notice anything that's useful or interesting that isn't seen in anybody, so they give up. But then both computers get better and observations get better, and you have to reassess, and then probably, or at some point, it will become useful.
Yes, you've hit the nail on the head. That's exactly the problem here, and so that's why I really hope that this direction will continue, because I think it's going to be very, very interesting. I'm not trying to downplay what's been done so far. There's been great studies that have used these techniques. I just wish I could see many, many more. I want to fast forward 20 years to see.
I guess one of the big problems is that something like an n-body simulation is just so easy, and then because it was easy, it gained lots of results really quickly, and then codes and people became experts at that in the community, and then it's sort of like you just grandfather new generations who are also now experts at it because they learned from previous experts, whereas other techniques, yeah, that might be useful now don't have that kind of history behind them in the community.
Yeah, definitely. You have to keep being a little bit explorative. Otherwise, as you're saying, you get locked in this sort of communities. And I mean, it's great, obviously, what work you do there, but at the same time, those approaches have limitations, and we know very well what they are.
Okay, cool. Thanks everyone for watching. If you liked this, then please do subscribe and click the bell if you want to be notified of new videos. And click like to help with YouTube algorithms, and share the channel with your colleagues. If you have any questions or suggestions, leave a comment. I'll make sure that Eloisa sees them. And other than that, thanks again, Eloisa, for the great talk.
Thanks for having me.